There are many libraries available for generating statistical charts, and many of them have galleries online that show the variety of charts that they can generate. So these galleries can be useful for helping programmers to understand the expressiveness of a given library. There's at least one website that allows us to see for a given chart type how to implement that chart in a whole variety of libraries. So this is sort of like a Rosetta Stone, allowing us to translate a specification of a chart from one library to another. We can extend this idea even across languages. So here we have the same type of chart showing the same data using two libraries in two different languages. I've been saying library over and over, but some of these things are more properly referred to as grammars or domain-specific languages. So we'd like to have a more general term for these things, so we're going to call these things notations. And in particular, we're going to be interested in the 9 notations that we have listed here. So how do we evaluate a notation or compare two notations? There's a few approaches that are possible. We might simply look at galleries of examples generated with each notation, but these galleries tend to contain different examples, which makes it difficult to compare notations. There's at least one theoretical framework for evaluating notations, and that's the cognitive dimensions of notation. So this is a whole set of properties such as the economy of the notation, the terseness, the viscosity, and these can be used to perform evaluations, but this requires a certain amount of skill or expertise, and there's a certain amount of subjectivity involved. We could perform an empirical evaluation where we ask participants to implement charts using different notations, but that takes time and it's costly. So we propose a new method where we have metrics that can be computed algorithmically, and they allow us to compare notations objectively. And some of the metrics that we propose capture some of the ideas in the cognitive dimensions of notation. So we chose a set of 40 visualizations, and we implemented each of these in each of the 9 notations that I mentioned earlier. And we get this big table, which we call a multi-notation gallery. Each column is a notation, each row is a visualization, and each cell in this table has a specification in source code that generates the thumbnail that we see. We could take 2 specifications in a given notation. So for example, in Seaborn, we might take 2 charts and their specifications, and we might be interested in how different the specifications are, because this is related to the idea of viscosity and the cognitive dimensions of notation. So the idea of viscosity is how easy is it to get from one specification to another? How much do you need to change the specification? Right? So to compare these 2 specs, we could simply compute a diff between the specs. And if we do that, we find that there are certain differences between them that I've highlighted here. And by counting these differences, we can count the number of things that need to be changed to get from one spec to another. And this is essentially the Levenshtein distance, Levenshtein edit distance between these 2 specs. So that's one way to quantify the distance between 2 specs. Another way to quantify the distance is using a compression algorithm. So if we have a way of taking the text of a spec and compressing it, we could compress each of the specs on their own and take the minimum resulting length and then subtract that from the compressed length of the concatenation of the 2 specs. And then we get what we call the compression distance. It turns out that this is very correlated to the Levenshtein edit distance. In the results I'm going to show you, we might be using Levenshtein sometimes and compressed distance at other times. So one thing we can do now that we have this way of computing distances between specs is we can take all the specs in one notation and compute a distance matrix. That is to say, we compute the distance between all pairs of specs, and we end up with a weighted complete graph. Now that's quite a dense graph, so we played with different ways of showing something simpler. For example, we took the complete graph and we reduced it to a spanner graph, which has fewer edges. And you can see the numbers on the edges show distances. In this case, it's Levenshtein distances. But the result is still difficult to read. It's still rather hairy. So We could remove even more edges and just end up with a minimum spanning tree. And again, you can see distances along the edges. And we start to get some sense that some of the specks are more central, maybe around here, and some of the other specks are more distant from that center. So they're more like outliers. And in fact, one of the metrics that we define is called remoteness. So the remoteness of a speck is the median of the distance from that speck to all other specks. Okay, so a speck that's very remote is very far from the center. We could also take the data associated with the distance matrix and apply multidimensional scaling. Again, we see a sort of central cluster and some other ones that are more remote. A dendrogram is another way to show the same information. And here what we've done is plotted all 9 notations. So for each notation, we show all of the specks plotted so their x position shows their remoteness. What we see on the left here is 3 of the notations look quite different because they have a lot of specks that are very remote compared to the central body of specks. So those 3 are matplotlib, pandas.plot, and plotly.go. And those 3 we're going to hear about again in a few slides, how they are different from the other notations. What we have over here is we've counted the number of times that different tokens appear in the different specs. So in a given notation, there's a set of tokens, unique tokens that are used in that notation. Some of these tokens appear quite commonly across different specs, and some of them are very rarely used. So for example, in matplotlib, there are 45 tokens, each used in only one spec. There are another 40 tokens that are each used in 2 specs, and so on. There's another 18 tokens that are used in every single one of the 40 specs. So we can get some sense of the distribution of tokens by looking at these bars. I'm going to show you now a more complete set of all the metrics that we use in our paper. And I'm going to relate these metrics to ideas from the cognitive dimensions of notation. So the cognitive dimensions of notation will be listed on the left here. One of the cognitive dimensions is economy, the idea of a notation that is economic, is a notation that is efficient in the words or the symbols that it uses. So we simply count the number of tokens in a notation, and we call that the vocabulary size. That's how we quantify the economy of a notation. Another cognitive dimension is terseness. So how short is a specification? That's terseness, and we capture that simply by looking at the length of a specification, and we simply compute that in bytes. So we count the number of bytes in each spec. Now we can also compute the terseness of a notation by looking at the median length of the specs in that notation. Another idea which I showed earlier, that is the idea of a distance between 2 specs, between a pair of specs. So that captures the idea in the cognitive dimensions of viscosity. How difficult is it to get from one spec to another? So now that we have a distance between a pair of specs, we can then talk about the distances associated with a single spec, and that's remoteness, which I mentioned earlier as well. The remoteness of a spec is the median distance to all other specs. And then finally, we can quantify the distances associated with a single notation, and we call that the sprawl. So the sprawl of a notation is the median distance between all pairs of specs. Now let's think about these 3 metrics associated with each notation. Let's think about the relationships that we might expect to find between these metrics. If we think by analogy with a spoken language, in a spoken language, if I have lots of words that refer very precisely to different objects and concepts, then I should be able to say more with fewer words, right? I should be able to express a precise idea using few words because each word will carry more information. So intuitively, if I have a larger vocabulary, more words to work with, each spec, each sentence in some sense, should be shorter on average. So I expect an inverse correlation between vocabulary size and median spec length. We could also expect that if the specs in general are longer, so if the median spec length is bigger, then the distance between any 2 specs might be larger because there's more symbols, more tokens involved. And so to get from one spec to another, will probably involve changing more of those tokens, and therefore it'll involve a bigger distance. Bigger distances means a bigger sprawl. And now if you accept these two ideas, what these two ideas together imply is that the vocabulary size should be inversely related to the sprawl. What we can do next is for each of our 9 notations, each of these 9 colors, for each notation we can compute the sprawl of the notation, the median spec length, and the vocabulary size. And then each of these notations becomes a point in each of these scatter plots. Now maybe there was some bias in the way that we chose the visualizations in our multi-notation gallery. Maybe there is also some bias in the way that we wrote the specs for our multi-notation gallery. So to try to mitigate some of that bias, we took subsamples of the multi-notation gallery and computed a whole set of points for each of these, and then used kernel density estimation to find these contours. This gives us some increased confidence about where each of these notations is located on these plots. And we can see that some of the notations do appear to be quite different from others. In fact, we identify 3 subsets of notations, and these arguably correspond to 3 categories of languages for describing visualizations. So Wang Supasawat described these 3 categories in previous work as high-level composition, chart templates, and grammars. And they do appear to be separated in the plots that we have here. We can also come back to the expected relationships between these 3 quantities and check to see if any of these are confirmed. And it turns out largely they are not confirmed. So vocabulary size versus median spec length, that would be in this plot, and if they were inversely related, we would expect to see the data, the notations along a line something like this, and that's not what we find. Median spec length and sprawl, if this second bullet here was true, we would expect to see the notations line on a line something like this, and that seems partially true, partially confirmed, but not clearly confirmed. And then the last expectation here was that vocabulary size would be inversely related to sprawl. That would correspond to a line like this in this plot, and that's the opposite of what we see. So in our paper we go into some possible reasons for why we have these results instead of these ones. We also report the results of interviews that we conducted with 6 experts. These are people who actually wrote or maintain prominent charting libraries. And there's additional information online. There's a source code for our Notoscope tool. There's a live web-based demo of Notoscope, and there's a video that shows how to use Notoscope. So just to sum up our contributions, what we propose in this work is a way of evaluating and comparing notations using metrics. And to do that involves the idea of a multi-notation gallery and also specific metrics that we proposed, namely remoteness and sprawl. And these metrics allow us to compute things about the gallery. We also report the results of interviews with experts, and we contribute the Notoscope tool. Thank you to everyone who helped us, and thank you for your attention.